Hello everyone. 2 days ago on CES 2025, Jensen Huang introduced several new products from Nvidia that amazed the AI industry. One is their Open World Foundation Model platform. Today I'm going to introduce this Open World Foundation model developed by Nvidia. Nvidia has opened up the models and the technical report. Please watch a short video generated by it first. It looks realistic and can have great practical values for physical AI. Now let's get into the technical report. So the introduction today includes the following parts. I will first talk about what the World Foundation Model is and its purpose, then the data curation part and tokenization and modeling, including pre-training and post-training, and then lastly I will talk about the limitation of the current model. In this paper, another part is about the guardrail. I don't think it's very interesting, so it will not be included in the video. Now let's talk about what the World Foundation Model is. Basically, it's a video generation model. To put it simple, it is conditioned on text input and previous frames or other signals. So one thing that makes it stand out from a general video generation model is that it tries to reflect real-world physics, not just generate any kind of videos, such as for gaming or animation. And another feat is that the videos generated by it are always within the same shot. And the reason it makes the model generate videos only following those constraints come from its purpose. So the purpose is to create a digital twin of the real world, and the model is built for physical AI. Physical AI refers to AI models that aim to interact with the physical world as opposed to the digital world, like ChatGPT or other language models are for. And the World Foundation Model can provide a very realistic environment to train or evaluate physical AI agents. So we can develop physical AI without letting them interact in the real world prematurely. This is because interactions like experimenting in the real world may cause damage to the AI system or the real world before they are properly trained. So training them in a simulated world can avoid this kind of trouble. And there is already research trying to train physical AI models using Unreal Engine simulated environments, or more commonly using simulators for reinforcement learning agents like those provided in OpenAI Gym. The difference is that the environment provided by this World Foundation Model is not hard-coded, but simulated or generated by an AI model. Okay, let's talk about how they train the model. First, they curate a video dataset. In the video dataset, they want to make it very diverse and cover different environments. So here it shows the percentage of different environments or scenarios. And the data curation goes through the following steps. First, as I said, they train the model to generate videos that are continuous and in one shot, so they split videos into shots that are at least 2 seconds and at most 60 seconds long. They discard shots that are shorter than 2 seconds and split long shots into 60-second intervals. And they use a neural network called Transnet V2 to identify the boundary between different shots in the video. The second step is to filter the videos they got from the first step. They filter based on motions. So they don't want videos with unstable motions, like videos shot with handheld cameras, and they tag the motions of the video, like what kind of motions are present in the video. And they filter low visual quality videos. And for some videos, there are text overlays, like captions, which they don't want because in real world, there is no text floating in the air. So they auto filter out those. And for video types, they don't want non-real world videos like animations or gaming environments. Then the next step is to annotate the videos. So they want each video to have detailed captions. Later, when they train the model, they take those detailed descriptions as input and the video as output. So they generate the captions using some proprietary models. And lastly, they perform deduplication. They don't want duplicate video clips in the dataset for a more balanced and diverse data distribution. Then the next step is about tokenization. So they tokenize the video clips so that the video samples can be processed by AI models. There are two kinds of tokenizations they tried. One is continuous tokens, and one is discrete tokens. So they are shown in those two images. As you can see, in the continuous tokens, each token is actually a vector, yet they call the vectors tokens. And the way they do it is that they break the frames into blocks. So each block corresponds to a small piece of the whole image with a fixed size in multiple continuous frames. That means each token corresponds to a vector representing a small piece of the video across multiple frames. Here, for the discrete tokens, it's the same, but each block across multiple frames is represented by multiple discrete tokens. So each token is an integer corresponding to the index of an embedding in a codebook. Overall, the tokenization works like this. There is an input video, and the tokenizer encodes the video into tokens, and the tokens form a 3D array. Each element in this 3D array is a vector if it's a continuous tokenization, and it is a list of integers if it's discrete tokenization. And then they can be decoded back into the to reconstruct the video. And the reconstructed video should be as close to the input video as possible. About the architecture of the tokenizer, they call it Cosmos tokenizer. So it's a lightweight and computationally efficient architecture that has causal temporal convolutional layers and causal temporal attention layers. Here, the causal temporal attention is like the attention in GPT-like language models, where later tokens can pay attention to previous tokens, but not the other way around. For the convolutional layers, it's the same idea. For the computation of the current token, the filters can go from previous frames to the current frame, not further. So here, they show the evaluation of their tokenizers, including the continuous tokenizer and the discrete tokenizer. At the same spatial temporal compression rate, their Cosmos tokenizer performs better than existing tokenizers in the reconstruction quality. Now let's talk about the world foundation model and pre-training. They propose two frameworks. One is diffusion-based models, and the other is autoregressive-based models. They are for continuous tokens and discrete tokens, respectively. This aligns with the common approach in modern AI. For continuous tokens, or let's say vectors, they often use diffusion-based models, and for discrete tokens, they use the autoregressive-based models, as in language modeling. So let's go through the diffusion-based models first. Here the input is the video, and the tokenizer turns the video into a 3D array, and the authors add some Gaussian noise to the tokens. Then they employ a 3D patchifying process. Basically, they apply a linear mapping to each token and then reshape the 3D array into a 1D array. Then they apply positional embedding to the tokens before the self-attention, because attention layers require positional information. They use a 3D version of rope, which is commonly used in modern language models, to capture the position of a token in the 3D array. The difference is that this is a 3D version. So the position of a token has 3 elements, and they also use absolute positional embedding, which is like a trainable embedding layer, as in GPT-2. They employ this absolute positional embedding is because they find that adding this embedding layer can improve the performance. And then they use one self-attention layer and then one cross-attention layer to the text prompt, so that when you generate, the output frames are also conditioned on the input text. And like in a transformer block, there is an MLP in each transformer block, and there are n such transformer blocks. And for diffusion models, the output of the model is the denoised token. So it is the denoised vector of the current frame, and they repeat this process for a fixed number of diffusion, or let's say denoising steps. Eventually they get the denoised tokens, which are vectors, and those tokens are then fed to the decoder of the tokenizer to reconstruct the new frames of the video. Next, let's talk about the autoregressive based model. So the input is still tokenized into a 3D array, but in this array, each element is actually multiple integers to represent a block of the video. And then they use a vocabulary embedding to map the tokens to their vectors and reshape the token arrays into a 1D array. And they also apply 2 kinds of positional encodings. One is rope, one is the absolute positional embedding. And yes, then they apply self-attention and cross-attention, where the cross-attention is to the input text, then an MLP in each transformer block. They have n layer transformer block, and the final output will predict will be the prediction of the tokens for the new frames. And they decode the tokens with Cosmos Tokenizer to reconstruct the new frames of the video. And they have one more component called the prompt upsampler. This is required because the world foundation model is trained with detailed descriptions, but the user's prompt to generate a video could be very different, like low quality text or short descriptions. So it follows a different distribution from the training prompt. They apply a prompt upsampler, which is fine-tuned Mistral Nano 12 billion instruct model that takes the user's prompt as input and generates a detailed description, similar to how ChatGPT might expand a simple prompt for image generations for the users. Now let's talk about the post-training. So the post-training part is more like applying the pre-trained world foundation models to different scenarios. One is about camera control, where they annotate the relative camera poses of videos using existing models and train the model to generate frames conditioned on the camera pose information. Another example of post-training is for robotic manipulation. There are 2 kinds of video predictions. One is instruction-based video prediction, where the input is the current video frames of a robot and the text, the instruction that tells what the robot should do. And then the model predicts the next frames showing how the robot followed those instructions. And the other kind of robotic manipulation is action-based video prediction, which uses the current video frame of a robot and an action vector between the current and the next frame to predict the outcome of the action. So it outputs the predicted next frames showing the result of the action. The way to create a dataset for this is that For instruction-based video predictions, they create an internal video dataset called Cosmos 1X dataset. They actually used humanoid robot from 1X, which is a company that produces robots, and they captured the video with if, and this way they have over 200 hours of egocentric videos. And for action-based video predicting training, they use a publicly available dataset called Bridge. Then the next application is autonomous driving. So they create a real driving scene dataset comprising approximately 3.6 million 20-second surround video clips. Each clip is recorded with 6 camera views: front, left, right, rear, rear left, rear right. And in each frame, the model has all 6 cameras images. And they train 3 multi-real world models. One is a text prompt input. So that it's a text to world model where the text that the text describes the environment and what happens. And the second is built on the first one, adding trajectory input. And the third takes video frames as input and it generates subsequent frames. So this model can take the output of the first or second model as its input to generate the complete video. Okay, here I summarize it. In this table, it shows 2 types of models: diffusion models and autoregressive models. So they trained diffusion-based models include 7B and 14B, and the autoregressive models include 4B to 5B and then 12B to 13B versions. So there is a 1 billion parameter difference between those 2 autoregressive model versions, because the first one doesn't include a text encoder and the second one does. So in the middle and the right columns, it shows the tokenizers and the prompt enhancer they used for those models. Here I summarize the limitations of the models. The major one, I think, is about modality coverage. So as a world foundation model, you need to encompass all modalities. But here you only have vision, no sound or odor. But those things are important for AI agents because they need to be able to use sound, odor, or touch, etc. to understand the physical world and make actions. So to train a physical AI agent, you need those sensors, and in a world simulator, you need to provide them those things as well. And then the other limitation, I think, is the performance of the model still needs improvement to be practical. And the authors kind of admit this in the paper. That's all. Thank you very much for watching. The link to the paper and to the GitHub repository and the Hugging Face page are given in the descriptions below.